This lesson continues our discussion on the central limit theorem. What we want to talk about now are the middlemost usual sample means. That is to say, we will pick some percentage to be the usual range, and we will ask what sample means would fall in the middlemost range. What we are actually doing is foreshadowing the concept of the confidence interval. A lot of the mathematical machinery we will be setting up in this analysis will support our discussion about confidence intervals once we formally introduce them. First, let's start with the standard normal distribution. Recall, when we have the SND, we can connect this information back to any normal distribution via conversion to z-scores. Let's start with a sketch of the normal distribution. We know this is centered at 0. We know this because it is a standard normal distribution. Furthermore, we know that the standard deviation is 1, so 1 unit is 1 whole standard deviation. What I would like to do now is to locate the interval in which we would capture the middlemost 90% of all z-scores for a normal distribution. So there are some boundary values just beyond each inflection point, but probably not all the way to 2 whole standard deviations above and below the mean. Inside these boundary values, the area under the curve would be 90% of the total area under the curve. This means if there is 90% in the middle, there is 10% left over. So in each of these two regions below and above the middlemost region, we will find the remaining 10% of the area under the curve. And because of the symmetry of the normal curve, there would be 5% in the lower tail and 5% in the upper tail. The question is, how do we locate these values? Or better, how do we find the z-scores for these values on any normal curve? This lower tail is probably the most straightforward to calculate, so let's start here. I'm going to label this z sub L for lower, and we can call the other value z sub U for upper. So we are looking for the lower boundary and the upper boundary. By the empirical rule, these values should be about 5/3 for the middlemost 90%. But the empirical rule is just an approximation. We now have the tools to calculate these values exactly. So we will enter into Excel NORMSINV, and we do indeed want the S function in this case because we are talking about the standard normal distribution. I'll enter the value 5%, and that will return the value negative 1.644 and change, but with rounding, this would be negative 1.645. Again, this would be the lower boundary separating the lower 5% of z-scores from the remaining upper 95%. Now, I could punch a formula into Excel to get z sub U, but I could also use the symmetry of the SND about the mean, which is 0. What will z sub U be? Pause the video briefly to reflect on what this would be. We see that we don't actually have to do any math or calculating to get this value, because all we need to do is change the sign from negative to positive. The magnitude of this value is just the same as the lower boundary value. Now, for those students who might not be comfortable going back and forth using the symmetry or the geometry of the normal curve, you can punch this into Excel. To put this in Excel, we would enter NORMSINV, and now because we want the upper 5%, this is essentially the same as asking for the lower 95%, which is the percentage of the two lower regions added together. In fact, I could enter this in Excel as 5% plus 90%. You also could just type in the sum of 95%. If you do this in Excel, you can confirm that you do indeed get the same value as before, just without the negative sign. So z sub upper is positive 1.645. One of the questions on WAMAP that causes students some challenge is the question that asks students to first calculate the z-scores of these boundaries, but this appears after we've been using the more advanced Excel function that bypasses the need to first calculate the z-score. We will introduce that function next. However, it is always the case that you can ask what the range of usual z-scores would be for your problem. Then you can convert your current observation from your sample data to a z-score, and you can ask if that z-score that you observed falls in the range of usual values or not. This is always a possible approach that we can fall back on. But to take advantage of this approach, we need to recall that the z-score is our data value less the mean, all divided by the standard deviation. So if I want to solve this for x, I would multiply both sides by sigma. The sigma on the right side cancels, and we are left with z times sigma equals x minus mu. If we add mu to both sides, we get the formula mu plus z times sigma equals x. This is the formula I can use to find the boundary values in terms of x if I know the boundary values in terms of z-scores. If I know the value of z, my z-score, i.e. how many standard deviations my value is above or below the mean, if I also know the mean and standard deviation for my distribution, then I can go backwards and calculate my actual value. So using these boundary values here, negative 1.645 and positive 1.645, what I want to do is compare the population compared to the sampling distribution. This will use the pictures that are available to you on WAMAP for this lecture. See the handouts folder in this current module. So what we want to do is answer both of these questions. What are the boundary values for a single observation, and what are the boundary values for sample means? This upper plot is a much cleaner drawing of what I just drew for you. Now we will ask, between which values would you expect to find the middlemost 90% of all IQs? So this blue graph is talking about the population of all IQ scores. Whereas the second problem, which is very similar, asks, between which values would you expect to find the middlemost 90% of all possible sample means of IQ scores? The first thing to note is that for our second problem, we are talking about a specific sample size. For this problem, we are talking about samples of size n equals 120. This is a value that would have to be given to you in the problem, and I'm telling you here that this is n equals 120 for this problem. The other important thing to remember that this is the sampling distribution, whereas up here we have the actual population distribution. The population is in blue and the sampling distribution is in orange. Regardless of the numeric values along each of these two horizontal axes, I know that the z-score for each of these boundary locations is negative 1.645, and the upper boundary is at a z-score of positive 1.645. In other words, these boundary values on each of these normal curves are 1.645 standard deviations above and below the population's respective means. Let's walk through the calculation for each of these problems. So what we want to do here is we want to focus on the blue graph. Okay, so we're focusing on the blue graph, so we're talking about the individual here. What I know for the distribution of individual IQ scores is that the mean is 100 and the standard deviation is 15 and the distribution is normal. I also know the upper and lower boundary values are at z equals plus and minus 1.645. Z lower is at negative 1.645 and z upper is the same value but positive. It is at positive 1.645. So if I wish to locate the actual boundary values for possible IQs, the lower boundary for the IQ scores would be 100, the population mean, minus 1.645 times my standard deviation, which is 15. And if we punch this in a calculator, we should get 75.325. I can repeat the nearly exact same calculation to get the upper boundary value. This time, we replace the negative z-score with the positive z-score. Change to positive 1.645. Not surprising, this is the same distance below 100 as this value is above 100. There is a certain symmetry here. Going back to the slide, we can indicate the boundary values. The range of values in which I would find the middlemost 90% of IQ scores would be 75.325 and 124.675. This is the range in which we would expect to find these IQ scores, the middlemost 90% of all IQ scores. And we can see on this graph that this is a pretty reasonable accounting for the values indicated. However, this is most likely not how you would do this calculation. In most cases, we can skip the intermediary step of calculating the data score from the z-score. To do this, we should use the NORMINV function, not NORMSINV. We would enter NORMINV 5%, then we enter the mean and the standard deviation for a total of 3 arguments for this function. The mean is 100 and the standard deviation is 15. This will give us the desired value. This will skip calculating the z-score, and this will give the final answer straight away. Likewise, the formula down here would be 95%. 100 for the mean, and 15 for the standard deviation. Thus, I don't need to calculate the z-score along the way. If you do for the first handful of problems, it will help solidify an understanding of what is happening, and it will help you understand how you might go back and use the z-scores. But in all truth, this is the far more efficient approach. In fact, I'm expecting most students will use this formula in Excel and will use this approach to solve problems like these. The advantage is that you don't have to calculate the z-score and convert that to a raw score. In fact, this may result in fewer errors as there are less calculations that have to be worked out. Of course, every student internalizes this differently, so you now have a couple of avenues by which you can tackle these problems. Let's return to the picture. Previously, we found the middlemost range of values in the population. Now we are asking, if we have samples of size 120, what is the range of the middlemost 90% of means we would observe? Next, we will focus on the orange part of this problem. I will retain most of what is on this whiteboard, but we will add the additional information that the sample size is n equals 120. We will also remove the attention from the individual, and we will now direct our focus to the mean. If we take this information here, we can conclude the following. The mean of the sample means is just the mean of the population, that is, the same value of 100. But the standard error, the standard deviation of my sample means, that would be sigma over the square root of the sample size. In this case, 15 over the square root of 120. Numerically, we could calculate an estimate for this. It would be about 1.369 and change. But using Excel, I'll see that I don't actually have to calculate that intermediary value. So everything in our formulas here remains the same, except we won't have the values 15 in these two spots. Instead, they will be replaced with the value 1.369, which means, in turn, these numbers are no longer the same. These new values would actually be 97.75 and 102.25. Now, let's look at how we would revise this Excel formula to get our desired result here. For this formula, we would still enter 95% because this is the boundary percentage for the middlemost 90%. And we would still enter 100 because that is the mean for this distribution as well. But now, for the standard deviation, I wouldn't bother entering the number because I can just let Excel do the calculation for me. I would enter 15 over the square root of 120. In Excel syntax, this is 15 over SQRT 120. Actually, in truth, I would be more inclined to enter in cell A1 the formula equals 15 over SQRT parenthesis 120 close parenthesis. Then in my formula here, I would enter the reference to cell A1 for the standard deviation. And I can do the same thing up here. I would enter 100 and the reference to cell A1, which is the standard deviation for this distribution. The other nice feature of this approach in Excel is that this completely counts as, quote-unquote, showing your work, particularly when a problem on a quiz or test needs you to show your work. So submitting an Excel sheet with these calculations would count as showing your work for my class. So let's go back to the slides. Now we can record our values here, 97.75 to 102.25. And we note that the range is noticeably smaller in size compared to what it was for the population. The span of the range for the population is about 50 IQ points, but the span for the means is only about 5 IQ points. And this is a direct consequence of the fact that the distribution of the sample means is much less spread out compared to the distribution of the population. A common question students have when learning about normal distributions and the central limit theorem is, how do we tell the problems apart? In other words, what clues are there for when we should use the central limit theorem? Anytime we are talking about the probabilities associated with a sample, this is the major clue that we should be working with the central limit theorem. Notationally, if we saw a problem that looks like this, what is the probability that x is at most 95, given that we know the mean to be 100 and the standard deviation is 15? First, we notice that no sample size was given. So this clues us in that this would not involve the central limit theorem. On the other hand, if we have a problem asking for the probability of a sample mean of at most 95, in this case, the moment we see that we are talking about a mean, i.e. information from a sample, this means we should use the central limit theorem, and in particular, we should look for the sample size. So anytime you see reference to any of these three things in a problem, the mean, reference to a sample, or a given sample size, these are the clues that you should be working with the central limit theorem. If you can't see a sample size anywhere in the problem, this is a clue you are not working with the central limit theorem. On the other hand, if the sample size is indeed given, you probably are doing a central limit theorem problem. Once you have confirmed you are indeed working on a central limit theorem problem, be sure to note the sample size. Say our sample size is n equals 25. Then we can calculate the mean of the means, which is the same as the mean of the population, and we need to calculate the standard error, the standard deviation of the sampling distribution, using the formula sigma over the square root of n. For us, that would be 15 over the square root of 25, which is 15 over 5, or the value 3. So these are the clues to determine if you should be using the central limit theorem. Let's compare the Excel functions for these two probabilities. Well, I say Excel functions, but it really is the same function. We are just entering different things into it. So our first function for the calculation here in purple equals NORMDIST parenthesis. Then we give it the value 95. Next, we would punch in the mean and then the standard deviation, and we always say true. The mean is 100 and the standard deviation is 15. This would give us p of x less than or equal to 95 is about 36.9%. What changes for the next problem in fuchsia is the standard deviation here, 15, changes based on the central limit theorem. Everything is the same, but 15 is replaced with 15 over SQRT 25. And that would give us our new value. The way I would enter it would be in a manner that more clearly shows my work along the way. In cell A1, I would enter equals 15 over square root of 25. In cell A2, I would enter equals NORMDIST 95, 100, A1, true. This is what I would enter in Excel, and it would give the desired result for the probability that the mean is less than or equal to 95 for samples of size 25. And the probability here is only 4.8%, which is noticeably less than our previous probability of 36.9%. From here, we can talk about one of the consequences of the central limit theorem. Let's retain these probabilities. The probability of a mean of at most 95 is 4.8%, and the probability of an observation of at most 95 is 36.9%. A consequence of the central limit theorem is this. As the sample size goes up, the probability for a question such as this gets smaller. As n increases, or in other words, as n gets bigger and bigger, this probability of a sample mean, which is less than the population mean, this probability goes down. How much does it decrease, or how rapidly does the probability decrease? Well, let's look at the probability of finding a sample of at most 95 when we are working with samples of size n equals 2500. If I punch this into Excel, I get this output, 1.145 E negative 62. Recall, this is scientific notation, and it means we need to move the decimal place 62 spots to the left. This would be the value 0.000 ... 1145, where I had to move the decimal place 62 spaces. So there are 61 zeros here in this number. So we are talking about a very small number. It is technically bigger than 0, but for all practical purposes, it is essentially 0. The likelihood of this ever occurring is just short of impossible. Here is the end of class question for this point in the lesson. Give the Excel syntax for this calculation. In other words, what would I have needed to enter in Excel to get this result? There is more than one way to do this, so please be precise and concise in your answer. And this then ends our discussion on the central limit theorem for now. The next module will explore other types of sampling distributions we might encounter.